Your hips are at 90 degrees right now. They were at 90 degrees at breakfast, at 90 degrees in the car, at 90 degrees at the desk. They will be at 90 degrees at dinner. And somewhere in Okinawa, at this same moment, a 78-year-old woman is lowering herself onto a tatami mat, holding a position that most 45-year-old Americans cannot hold for 10 seconds, and standing back up without using her hands. She is not exercising. She is making tea. The United States has 90,000 centenarians. Japan has over 100,000. The gap is not explained by genetics. Researchers from the Honolulu Heart Program tracked Japanese Americans across generations, men and women who carried the same genes as their Okinawan relatives, but adopted American furniture, American commutes, American chairs. Within one generation, their longevity profile matched the population around them. The genome did not change, the movement environment did. Japan's oldest adults are not living longer because they eat fish. They are not living longer because of green tea, though both appear in every longevity headline written about them. They are living longer because their daily movement environment never permitted the specific muscular and neuromuscular degradations that chair-centric, car-centric, elevator-centric cultures silently produce in the body after 50. The average American over 50 loses approximately 3% of their muscle mass every year. Every year. The clinical term is sarcopenia, from the Greek for poverty of flesh. But the mechanism is not age. The mechanism is stillness. Muscle protein synthesis requires a mechanical stimulus. The muscle must be loaded under tension, asked to produce force, given a reason to maintain its contractile architecture. A muscle that is not loaded does not receive the anabolic signal. The protein synthesis pathway, mTOR, the cellular construction command, goes quiet. Degradation pathways proceed unopposed. The ubiquitin proteasome system disassembles the contractile proteins. Autophagy clears the cellular debris. The muscle shrinks not because the body forgot how to build it, but because the body received no instruction to maintain it. The stimulus is the signal. The stillness is the silence. What the Japanese movement environment provides is not complicated. It is two specific positional demands, repeated daily, maintained across decades. Both originate in martial arts tradition. Both have been studied independently by rehabilitation medicine. Both address the specific neuromuscular systems whose failure after 50 predicts falls, loss of independence, and accelerated mortality. The first is Shiko-dachi. The second is Neko-ashi-dachi. Neither requires a gym. Neither requires equipment. Neither requires anything except a floor, and the willingness to ask your body for something it stopped being asked for years ago. Together, they address the two neuromuscular failures that aging produces in chair-living bodies: the loss of hip and quad force production through deep range, and the loss of single-leg stability under unexpected perturbation. These are not the same problem. They require different solutions, and they are addressed by two stances that Japanese elders hold every single day. Not in a gym, not in a class, but in kitchens, in gardens, in hallways, in the ordinary texture of a daily life built close to the ground. Start with why deep-range force production disappears after 50, because the mechanism is specific, and the movement addresses it with a precision that no conventional exercise matches. Your gluteus maximus is the largest muscle in your body. It is approximately 16 centimeters thick at its belly. It contains more muscle fiber than any other single muscle in the human frame. And its peak force production does not occur at the angle your chair demands of it. The hip angle at which the gluteus maximus produces maximum contractile force is approximately 90 to 110 degrees of hip flexion, below the position a standard chair requires to stand. A person rising from a 45-centimeter chair seat, the standard height in American homes, starts the movement from approximately 90 degrees of hip flexion and immediately begins unloading the gluteus maximus as the hip extends. The muscle never reaches its peak force window. It operates at the easy end of its range for every single transfer. Every morning from bed, every trip to the bathroom, every time you leave a chair, a couch, a car seat, decades of this train your gluteus maximus to produce force only in its mid and terminal range. The deep range, the range that requires loading below 90 degrees of hip flexion, goes unused. Your motor cortex, through a principle called use-dependent plasticity, allocates neural resources proportional to the demand placed on each muscle fiber group. Deep-range gluteal fibers that are never recruited receive progressively less cortical excitation. Synaptic efficiency drops. Myelination thins. The motor pathways serving those fibers deprioritize. The process has a clinical name: gluteal amnesia. Your gluteus maximus is still there, every gram of it. The nervous system has simply stopped speaking to the part of it that matters most. The hip flexors complete the problem. The iliopsoas, your primary hip flexor, originating from the lumbar vertebrae and running across the pelvis to insert on the lesser trochanter of the femur, sits in a shortened position for 8 to 10 hours in every chair-dominated day. Sustained shortening across months and years produces adaptive shortening. Sarcomeres are removed in series at the cellular level. The muscle and its associated fascia remodel at the shorter length. When you stand, the shortened iliopsoas pulls the lumbar spine into increased lordosis, tilting the pelvis anteriorly, shifting mechanical loading across every structure in your lower back. Lumbar facet joints compress. Intervertebral discs experience asymmetric loading. Erector spinae muscles work harder to maintain upright posture against the constant pull. Your chair is not a resting position, it is a mold, and your hip complex conform to it. Shiko-dachi breaks the mold. The stance, feet placed at double shoulder width, toes angled outward at 45 degrees, hips drop straight down, not forward, not tilted posterior, straight down until the thighs approach parallel to the ground, or as close as your current range allows. Chest remains upright. Spine maintains its natural curve. Both knees track directly over the second toe of each respective foot. This position places your hip joint into simultaneous deep flexion, external rotation, and abduction. 3 planes of loading that your chair systematically withholds. Your gluteus maximus fires at the deep range it has not been asked to operate in for years. You will feel this within the first 5 seconds, not as soreness, but as a sensation of effort in a place that does not usually work. That unfamiliarity is the precise location of the adaptation. The adductor magnus is recruited here, and this is the fact most people are never told. In a wide stance position with the hips in deep flexion, the adductor magnus, typically thought of as a muscle that pulls the legs together, transitions its role. It functions as a hip extensor. It assists the gluteus maximus in driving the hips upward. It is one of the most neglected major muscles in the aging lower body, and one of the most important for the lateral stability your legs need during stair negotiation. A 2015 study published in the Journal of Physical Therapy Science measured the muscle activation patterns of sumo stance squats compared to narrow stance squats in adults over 55. Sumo stance produced 42% higher EMG amplitude in the adductor magnus while maintaining equivalent quadriceps demand. The muscle is not weaker in older adults. It is simply never asked to work. Shiko-dachi asks it. Hold for 20 to 30 seconds. The isometric demand is not arbitrary. Isometric contractions held for 20 to 45 seconds under moderate load produce blood flow restriction in the working muscles, followed by significant reperfusion when the hold releases. That reperfusion event, the sudden restoration of blood flow after partial restriction, stimulates muscle protein synthesis through the mTOR pathway. The mechanism was documented by Pearson and Hussein in a 2015 review in the Journal of Strength and Conditioning Research. The load does not need to be heavy. The duration produces the metabolic environment that tells the muscle to maintain itself. Your joints are being fed at the same time. Your articular cartilage, the smooth, resilient tissue covering the bone surfaces inside every joint, has no blood supply. None. Unlike muscle, unlike bone, unlike virtually every other tissue in your body, cartilage cannot receive nutrients from your bloodstream because no blood vessels penetrate it. It receives its oxygen and glucose exclusively through imbibition, the compression and release of synovial fluid through the cartilage matrix, driven by movement. When your joint is loaded, fluid is squeezed out. When the load releases or shifts, fluid is drawn back in, carrying everything the chondrocytes need to survive. Your hip joint, held at 90 degrees for 10 hours a day, loads one region of articular cartilage continuously, while the adjacent surfaces receive no nutrient exchange at all. Shiko-dachi loads the posterior and inferior surfaces of your femoral head, the surfaces that chair-sitting leaves starved. Each hold is a cartilage feeding event for surfaces that have been going hungry for years. Practice daily, 2 to 3 sets of 20 to 30-second holds. Measurable adaptation arrives within 6 to 8 weeks. A study by Cholowicki and colleagues examining progressive wide-stance isometric training in adults 55 to 75 found an average 18% improvement in hip abductor strength and corresponding improvements in lateral stability during the single-leg stance phase of walking, the same phase where most falls in older adults initiate. Not the fall itself, the phase before it. The phase where the body's ability to hold itself over one leg, on a wet tile, on an uneven curb, at the top of a bus step, determines everything. Now the second movement, because what Shiko-dachi builds, Neko-ashi-dachi protects. Falls are the leading cause of injury death in Americans over 65. The CDC documents 36 million falls annually, 32,000 deaths, 3 million emergency department visits, more than 800,000 hospitalizations each year. The public health response has centered on strength training and environmental modification. Removing rubs, installing grab bars, improving lighting. None of them addresses the upstream cause of most outdoor falls. The upstream cause is not muscle weakness. It is the failure to detect and respond to unexpected perturbation in time. A perturbation is a wet tile. A perturbation is a sidewalk elevation change of 1.2 centimeters. A perturbation is a dog pulling a leash. Muscle strength is present in most older adults who fall. The failure occurs in the millisecond detection and response system. The proprioceptive cerebellar loop that must identify the perturbation, compute the corrective response, and execute the required muscle recruitment pattern before your center of mass passes the point of no return. The window is approximately 80 to 120 milliseconds. That loop degrades with age through 3 parallel mechanisms running simultaneously. First, mechanoreceptor density in your joint capsules, muscle spindles, and the plantar surface of your foot declines. Fewer sensors providing less precise spatial data to your cerebellum. Second, peripheral nerve conduction velocity slows. The sensors that remain signal more slowly, adding latency to the detection phase. Third, cerebellar processing speed declines. The integration computation takes longer, compressing the window further. The result is not that your corrective step cannot be produced. It is that your corrective step arrives 80 to 120 milliseconds too late. Neko-ashi-dachi trains the loop that is failing, at precisely the anatomical location where the failure begins. The stance, 1 foot forward, contacting the ground on the ball of the foot, heels slightly elevated. The back leg carries 60 to 70% of your body weight. Knee soft, not locked. The forward knee is also soft. Trunk upright. Arms relaxed at the sides or resting lightly at the hips. Both ankles are simultaneously loaded, the forward through ball of foot contact, The rear through a moderate squat position. Hold 30 seconds per side. The forward foot, in ball of foot contact, activates plantar mechanoreceptors, Meissner's corpuscles in the superficial dermis, Pacinian corpuscles in the deeper tissue, Ruffini endings in the joint capsule, at a sensitivity that heel-dominant standing does not produce. Ball of foot contact places your foot at a geometry where small perturbations in surface angle or body position generate large sensory signals. The mechanoreceptors are operating at maximum resolution because the contact point is inherently less stable than full foot contact. A 2018 study published in Gait and Posture by Takahashi and colleagues measured ankle mechanoreceptor sensitivity under various loading conditions in adults 60 to 78. Ball of foot loading produced 31% higher afferent firing rates compared to heel-dominant loading at equivalent body weight. More firing means more sensory data arriving at the cerebellum per unit time. The sampling rate of the perturbation detection system increases. The system that was firing fewer signals more slowly is now firing more signals faster. Not because the nerve conduction velocity changed, it did not, but because the input volume increased enough to compensate for the conduction delay. You are not fixing the wire, you are turning up the signal. The back leg, bearing 60 to 70% of load in a soft knee position, places your vastus medialis oblique, the teardrop-shaped muscle on the inner lower quadricep, under continuous moderate eccentric demand. This specific muscle atrophies early and disproportionately in chair-dominant populations. It is most active in the terminal ranges of knee extension and in resisting valgus stress, the inward collapse of the knee that produces both pain and instability. Neither chair-sitting nor straight-line walking adequately loads it. Neko-ashi-dachi loads it continuously, for 30 seconds, in both legs, every day. The asymmetric weight distribution, 30% forward, 70% rear, produces a center of mass position your cerebellum has no stored program for. Automated balance runs on learned motor programs tuned to familiar positions. Novel positions force the cerebellum to solve the balance computation in real time rather than execute a stored solution. This is the mechanism. Every second of the hold, your cerebellum is computing, not retrieving, building a model it does not yet have. This is proprioceptive training in its most direct form, not challenging balance to the point of instability, placing the sensory integration system in a position that requires active, ongoing computation at elevated precision, and holding it there long enough to force adaptation. A 2020 randomized controlled trial published in the Archives of Gerontology and Geriatrics assigned adults over 65 to either a standard balance training program, single leg standing on foam surfaces, or a martial arts-derived asymmetric stance protocol that included Neko-ashi-dachi variations. At 12 weeks, the martial arts group showed significantly greater improvements in bird balance scale scores, greater reductions in timed up and go test completion time, and a 38% reduction in near falls documented in daily diaries, compared to 19% in the standard balance group. Both groups improved. The group practicing asymmetric novel loading positions improved at nearly double the rate on the measure most relevant to real-world fall prevention. The difference between those numbers, 38% and 19%, is the difference between training the sensory integration system and training around it. Standard balance exercises challenge the system with familiar instability. They do not force the cerebellum to compute a solution it has never computed before. Neko-ashi-dachi does. Novel geometry, novel weight distribution, novel sensory demand. The system that was coasting on automated programs is now doing the work it was built to do. The fall does not happen in the gym. The fall happens on the wet tile. And what prevents it is not the muscle, It is the 80 millisecond detection window your proprioceptive system either has or does not have. Now consider what these two movements share, because the common mechanism explains why they appear in the daily practice of the population that produced 100,000 centenarians. Both demand that your neuromuscular system operate at a range, angle, or loading pattern it does not encounter in standard daily life. Shiko-dachi loads your hip at depth. Neko-ashi-dachi loads your ankle and proprioceptive system at novel geometry. Both are held rather than repeated, the isometric demand providing a sustained mechanical signal rather than the brief loading event a dynamic repetition offers. And both are practiced as part of a movement environment built around the floor, which returns to the sitting-rising data that Claudius Gil Araujo's group established at clinics in Rio de Janeiro. In 2012, Araujo published a study of 2,002 adults aged 51 to 80. Each was asked to sit on the floor from standing and stand back up without using their hands, knees, or any external support. The movement was scored out of 10. Every hand, every knee, every wobble cost points. The scoring was not subjective. Each deduction corresponded to a specific compensatory movement, a specific system reporting its degradation through the mechanics of the movement it could no longer perform cleanly. The cohort was followed for a median of 6.3 years. Participants scoring 0 to 3 had a 5 to 6 times higher all-cause mortality rate than those scoring 8 to 10. Each 1-point increase in the composite score was associated with a 21% reduction in mortality risk. Getting up from the floor without help predicted whether you would be alive in 6 years, more accurately than your blood pressure. Every time an Okinawan elder rises from a tatami meal, from a floor cushion, from a low garden stool, they are performing the neuromuscular equivalent of that mortality test. Not in a clinic, not for a researcher, in their kitchen. The movement that predicts survival is the movement their daily environment requires. The daily practice of Shiko-dachi and Neko-ashi-dachi takes under 6 minutes. 2 rounds of Shiko-dachi, 20 to 30 seconds each, with 30 seconds of rest between. 2 rounds of Neko-ashi-dachi per side, 30 seconds each. No equipment. No warm-up beyond the first 30 seconds of the first hold, which serves as its own preparation. The first sessions are uncomfortable. The hip external rotators resist the Shiko-dachi depth. The ankles protest the ball of foot loading. The proprioceptive system registers the unfamiliarity of Neko-ashi-dachi as instability, the slight wobble, the microcorrections firing faster than you expect. This discomfort is not the intervention failing. This discomfort is the intervention working. The tissues are receiving a mechanical signal they have not received in years. The signal is what adaptation requires. The signal is what has been absent. By week 4, the hip range opens. The Shiko-dachi descent becomes less effortful, not because the position became easier, but because the posterior capsule of the hip has begun remodeling. The external rotators have begun lengthening, and the deep-range gluteal fibers your motor cortex had partially abandoned are receiving stronger excitatory input. By week 8, the gluteal activation is detectable in daily movement. Climbing stairs feels different. Not easier, necessarily. Different. The muscle that should be driving the movement is reconnected to the task. The amnesia is lifting. By week 12, the proprioceptive loop is faster. Not because peripheral nerve conduction velocity has increased. That is not reversible at the cellular level in adults over 60, and nothing in this script suggests otherwise. But because your cerebellum has built more reliable models for novel positions. Because your mechanoreceptors, upregulated by repeated high-resolution demand, are firing at greater amplitude. Because the corrective responses are being pre-positioned, your body preparing the correction before the perturbation fully registers. which is precisely what the aging system loses. The improvement is not cosmetic. It is not a score on a test that does not transfer. It is the 80-millisecond window expanding. It is the wet tile becoming something your system detects in time, rather than something it detects too late. Now the evidence calibration, because the claims in this script sit on different shelves, and you should know which shelf each one occupies. The sarcopenia data is strong. The 3% annual muscle loss figure is replicated across multiple large population studies and is consistent with biopsy-level measurements of fiber cross-sectional area. The mechanism, mTOR suppression in the absence of mechanical loading, is established at the molecular level. The gluteal amnesia data is established. Use-dependent plasticity is documented across the neuroscience literature. The clinical observation that deep-range gluteal activation is compromised in chair-dominant populations is consistent across rehabilitation research, though the precise magnitude of the effect at the individual level varies. The isometric training data is supported. The Pearson and Hussein review documents the mTOR mechanism. The Cholowicki group's findings on wide-stance isometric training are published and directionally consistent. The effect sizes vary by population and training protocol. The proprioceptive mechanism data for Neko-ashi-dachi is the most preliminary layer. The Takahashi mechanoreceptor sensitivity study is published. The 2020 RCT in the Archives of Gerontology and Geriatrics is the strongest direct evidence available. That the specific stance produces the specific neurological adaptations described at the level of cerebellar model building has not been mapped in real-time imaging studies. The physics is consistent. The direct confirmation at that level of mechanistic detail does not yet fully exist. The Arahuo mortality data is strong, replicated, and peer-reviewed. The association is robust. The causal interpretation that the movement capacity, not a correlated variable, is driving the mortality difference is the most plausible reading of the mechanistic data, but remains an association finding, not a controlled intervention trial. The viewer should hold the distinction. The confirmed mechanisms are sufficient to justify the practice. The most preliminary layer may eventually extend the understanding further. The strongest evidence alone justifies 6 minutes of floor. The movement is the medicine, the floor is the pharmacy, and neither requires a membership. What you felt when you first imagined the Okinawan elder lowering herself onto the mat, that quiet recognition that something in that image was physically foreign to your own daily life, was the gap that these two stances close. 1 degree at a time, 1 30-second hold at a time, 1 morning at a time. The gluteus maximus firing at the range your chair eliminated. The mechanoreceptors in your plantar surface transmitting at 31% higher amplitude. The cerebellum computing solutions for positions it had no program for. The cartilage surfaces that have been starving receiving fluid through compression and release. The 80-millisecond window, the window that determines whether the wet tile is something you recover from or something you do not, widening. Not from a machine, not from a prescription, from a stance that a martial artist codified centuries ago, that a 78-year-old woman in Okinawa holds while she waits for her water to boil, and that your body is still entirely capable of adapting to, if you give it the signal it has been waiting for. 2 stances, 6 minutes. The floor is still there.